Here in section 5.2, what we're going to do is take that idea that we did in 5.1 where we were using in order to find the value of the area underneath the curve, what we did is we summed up several rectangles, and the rectangles are there to estimate what either the rectangles, if they went slightly above the curve, then they were an upper sum or an overestimate. If they went under the curve, they were a lower sum or an underestimate of the true value. And then we had the midpoint one, which kind of did a little average of the upper and lower sum and kind of got us a better idea of it. But looking specifically here at really what summing is, we have the shorthand for sigma. In sigma in math, we just use that saying, hey, we're going to sum up a bunch of terms. Specifically, if we look at this, when you see the term sigma, what all that is saying, get ready, we're about to sum up a bunch of things. We're going to start at one value, and we're going to finish at another value. And so, for example, if I said, let's do the summation from k equals 1 to 3, I'm going to plug 1 into this equation, like I did, and then I'm going to add, obviously, because we're summing, then k equals 2 plugged in, and k equals 3 plugged in. And if that all the way went up to 10, then I'd be adding up 10 different terms. So going on, here's a series of rules I'll let y'all just look through on your own, and some formulas, some easy ways, and so it's kind of a shorthand. If you ever get to those, instead of sitting there and have to add them up, you can just use this, especially if you're summing all the way up to 100. That gets to be a lot. Okay. The Riemann sum of a function over an interval that has been partitioned is defined as, okay, so the sum is going to be from 1 up to n, depending on how many intervals you have. And if you recognize this, look, it's the y value times the difference in x values. Just remember, anytime you plug a value into a function, you're getting a y value right there. Well, isn't that exactly what we did just a second ago in section 5.1? We were finding f of an x value times basically the change in x, plus like f of x2 times the change in x, and then just every single time the change in x was the same because we kept our intervals the same. Okay, so if we look at specifically this interval, it's saying xk minus xk minus 1. So this is a larger number minus a smaller number, or a number to the right minus a number to the left. Okay, and what it says below here, it says you're doing a lower sum if you choose the smaller one, the number on the left. You're doing an upper sum if you choose the number on the right or the larger value, and then the middle sum. Okay, I'll let y'all read a little bit more closely to that, but let's look at example 1. Here in example 1, we're just wanting to practice evaluating, so getting our feet wet with how to do summations. Okay, it says, first of all, we're going to plug, here's our starting value, so I'm going to plug that in first. So 1 minus 1 over 1. Then the next thing after 1, you always increase by integer amounts, so is 2. So 2 minus 1 over 2 plus 3 minus 1 over 3. And I'm going to stop right there because I've hit my final value of 3. So plugging this in and just looking or simplifying them, 1 minus 1 is 0 over 1 is 0. 2 minus 1 is 1/2, and then 2/3. So if I add all this together, we'll get a final value of 7/6. So the summation from 1 to 3 of k minus 1 over k is 7/6. Let's do the same thing with sine of k pi. So that'll be the sine of pi plus the sine of 2 pi plus the sine of 3 pi, sine of 4 pi, and the sine of 5 pi. And why I decided to put the angles in parentheses halfway down, I'm not sure, but I'm going to go ahead and keep it there. Okay. Well, the sine of any multiple of pi is 0, so 0 5 times is definitely going to be 0. And the last one here, just to get practice with, we're going to go -1 to the first times the cosine of pi plus -1 squared times the cosine of 2 pi. We're going to do 4 of these terms. So plus -1 cubed times the cosine of 3 pi plus -1 to the 4th times the cosine of 4 pi. Okay, so cleaning this up, we'll get -1 times the cosine of pi, which is -1, plus +1 times the cosine of 2 pi, which is +1, plus -1 times -1, plus +1 times +1. So we have -1 times -1 is 1, plus 1, plus 1 plus 1. So we get a grand total of 4. All right, let's go on to example 2. Which of the following sigma notations is basically going to express 1 minus 2 plus 4 minus 8? So it looks like all powers of 2, because this first one right here would be 2 to the 0, and that's 2 to the first, 2 to the second, and so on and so forth. But now we got to incorporate something that also tells it to switch its sign. Okay, my initial reaction is to want to go with that because at least it has 2 to the k as is. So let's check for this. Let's just play it. Let's just write it out. So negative 1 to the 0 times 2 to the 0 plus negative 1 to the first, 2 to the first, plus negative 1 squared, 2 squared, plus negative 1 cubed, 2 cubed. Let's just try with those just for a second before we get 4 and 5. So anything to the 0 power is 1, and 2 to the 0 is 1, so that's definitely a 1 right there. Negative 1 times 2, that would be a negative 2. Negative 1 squared is positive, so this would be 4. Negative 1 cubed is negative, so this is negative 8. And I'm thinking B's our winner. And if nothing else, if y'all want practice, go ahead and practice doing A and C just to get your feet wet, and then hopefully you'll see that B's the right answer. All right, example 3. We want to express the following in sigma notation. All right, again, it looks like 2 plus 4 plus 6 plus 8 plus 10. Okay, so we're not exactly powers of 2, are we? Because 6 and 10 are not powers of 2. So yeah, instead of looking at powers of 2, we're looking at just all of our even numbers. So how do we represent our even numbers? We're doing summation or sigma notation. Okay, well obviously we're going to do the sigma. We're going to start from k equals 1. We're going to go up 1, 2, 3, 4, 5 terms. Okay, we've got to think about this. So I want to multiply, like obviously there's going to be k in here. Well, look here, if I put 2 in front. Okay, so if I plug in 1, 2 times 1 is 2. That checks out. 2 times 2 is 4, then times 3, then times 4, and then times 5. So there's our sigma notation for this. It's just 2 times 1, then 2, then 3, then 4, and then 5. Okay, let's go on to this next one. First thing I noticed is that we're alternating in signs. We're going from negative to positive to negative to positive. So we've got to have something in our sigma notation that for sure is going to tell us to switch directions or switch our values, our magnitudes. 1, 2, 3, 4. We've got 5 values in there. And right away, look at the tops just real quick. The tops go 1, 2, 3, 4, 5. And they're all divisible by 5. So if I can just write k over 5, that's going to take care of it because that would be 1/5, 2/5, 3, 4, and 5/5. So that's great. All we have to do now is incorporate in there the sign change. Well, if I just do negative 1 to the k, just like that, then when I do to the first power, you'll get negative 1 to the first, which is negative 1. Negative 1 squared will make that positive, so my second term will definitely be positive. Third term, so all my odd terms are going to be negative, and all my even terms will be positive. So it looks like we got that one. All right, let's go to number 4. We want to evaluate this summation from k equals 1 to 6. So just getting practice. So it looks like it's going to be 3 minus 1 squared plus 3 minus 2 squared plus 3 minus 3 squared plus 3 minus 4 squared plus 3 minus 5 squared, and last but not least, 3 minus 6 squared. So simplifying this up, we'll have 2 plus negative 1 plus, let's see, 3 minus 9, so negative 6, plus negative 13, plus negative 22, and last but not least, negative 33. And then by the time we combine this all together, we'll get our summation to equal a negative 73. And there's your answer. Okay, again, let's get some more practice. This right here is going to be involving using the table of like properties for summation. So if y'all haven't looked at those properties, why don't you pause this for a second, go back up to the top, look at those notes again. So otherwise you're going to sit here and go, what in the world are you talking about? Okay. Okay, so here for part A, basically what we're doing is we have just a constant. We just have the number 4. And what we're going to do is we're going to sum it up from 9 to 36. So what y'all think about for a second is how many times are we going to sum this up? Do you just, how many, in other words, how many things are between 9 and 36? Well, the rule in general is if I just do 36 minus 9, which is 27, then I really haven't technically included both endpoints. 36 minus 9 would actually, which is 27, just includes really numbers 10, 11, 12, 13, 14, all the way to 36. So technically it's always your upper number minus your lower number and then add back on 1, so that way you can include both endpoints. So for 28 times, we're going to be adding 4. It's 4 plus 4 plus 4 plus 4 for 28 times. So in general, when we multiply that together, then the summation of 28 fours is going to be 112, and there's the answer. And here in part B, it's saying from 1 to n, so for n total times, we're going to be adding c. So c plus c plus c plus c. So for n times, I'm adding c, so the answer here is just nc. Okay. Now we have a formula. I remember if y'all looked at it closely or not, but we have a summation that says if I sum from k equals 1 to n of k squared, it's going to be n times n plus 1 times n plus 2 all over 2. Okay. That would be so awesome if I could use that, because I'm not really in the mood to go 3 squared, 4 squared, 5 squared, all the way up to 17 squared. But the thing is the different starting values. Here I'm starting at 1, and over here I'm starting at 3. Okay, why don't we go ahead and do this? Let's pretend it starts at 1, and then what we're going to do is just subtract off 1 and 2. That way we get from 3 to 17. Okay, so let's do this first. Summation from k equals 1 to 17 of k squared is going to equal n, which is 17, times 17 plus 1 times 17 plus 2 all over 2. Okay, so that's going to give us an answer.